This example is very similar to the example that we did with our piece of paper and the competition that we had, where you cut out squares out of the corner and tried to make the largest open-ended box that you could. So here we have a piece of cardboard that's 30 centimeters long by 25 centimeters wide. Ooh. And a great strategy in all of these word problems is to draw a picture to begin with to represent what we're doing. So we start with a piece of cardboard. It's 30 centimeters this way, 25 centimeters this way, and we're cutting out squares of side length x on the side. What that will do is once you cut that out, that will make a box. And if I draw that box using the color coding that I've done here, we would have a new length, which is this black side right here and here. We've got a new width, that is these red sides. And our height, which is x, is still this green part here. So now when we think about that box, once it's all been folded up and cut, we can label our sides. We know that this green side is that height is related to this square that we've cut out of the corners. The black length, well, it started as 30 all the way across, but this black length is now 30 minus 2x. And the red length, which started at 25, is now 25 minus 2x. So part A says, let's write a polynomial function of volume in terms of x. So we've got our picture drawn here. We know that our volume is length times width times height. And so in no particular order, that'll be x times 30 minus 2x times 25 minus 2x. And so this is a polynomial function. We have to decide when we want to graph this in part B, what kind of function is this? It's a positive cubic function. So how do we tell it's a positive cubic function? We can look at all of the x's. So I've got an x here, I've got one x here, and one x here. We've got no multiplicity in this question. Everything's a multiplicity of 1. And so we'll have x times a negative 2x times another negative 2x. That will give us an x cubed. Well, technically, it would give us a positive 4x cubed if we really wanted to be technical. But all we're worried about is figuring out what kind of function this is, and is that leading coefficient going to be positive or negative? And because it's positive, we know that our end behavior acts like a line. It's going to start in the bottom left and end in the top right. So now when we go to sketch this, it sure is nice that it's already factored, because since it's already factored, you know that you have an x-intercept at 0, which is also a y-intercept. What would make this factor 0? 12.5. And the last one, it would be 0 when x is 15. Now for each of those x-intercepts, will the graph go straight through, will it bend, or will it bounce? They'll go straight through on each of them because each of these has a power of 1. So it's going to start down here, straight through, and up here, and we've got our sketch of our graph. Now just like yesterday, this is the graph of that function, but when we think about our real-life example, the entire graph doesn't make sense. It doesn't make sense to have x values that are negative, because you couldn't cut out a square out of that cardboard with a negative length. And it doesn't make sense to cut anything out bigger than 12.5, because if you look at this rectangular piece, if you cut out 13 off of a square of 13 off of one corner, well, you couldn't cut a square of 13 off the other corner because there wouldn't be cardboard left. And then you wouldn't be able to make a box either. So I'm going to highlight that despite we've drawn the whole graph, this is the only part of the graph that makes sense. And so in part B, it says graph the function. What is the domain? The only part of the domain, the only part of this graph that makes sense is if x is between 0 and 12.5. And I don't include the equal signs because it doesn't really make sense not to cut out any square. You wouldn't have a volume that way. And it doesn't really make sense to cut out 12.5 because you couldn't make a box with that either. Although some people might argue, oh, then you have a box with 0 volume. Yeah. It just has no height. But I'm going to keep those equal signs off of there. For all practicality, it probably also doesn't make sense to cut out 0.00001, but we have to start somewhere. Then we're getting really technical. So now that we've got our graph, in part C, it says, to the nearest cubic centimeter, what is the maximum value, maximum volume? So another thing that I haven't done on my graph here is I haven't labeled things. So this is my x-axis. What did my x represent? It represented my height. And on my y-axis, I actually used v instead of y, so I'm going to put a v there. And it represented volume. So if we want to find the maximum volume, does it make sense that we're looking for that point right there? At this point, we're going to pull out our graphing calculators. It was really important that we first were able to graph it by hand, because when we type this into our calculator, so we got x, 30 minus 2x, and 25 minus 2x. When we put this into our calculator, because we've already got a sketch, we can go to our window and say, on my x-axis, I'm going to look from -1, just so that I can see my y-axis, up to, maybe I'll go up to 15. And what I'm really looking for is I would like to see this on my calculator. I want to see that part of my graph. So I started with changing my x from -1 to 15, because then I know that at least I have the correct width for my graph. And usually at the next step, you hit graph to see what it looks like. Oh. Apparently, I am looking a lot higher than I need to. Can you see that I have all this open space above? So to get a sense of how high you should make your graph, one of the things that's helpful is to go to a table of values. Now your graphing calculator above the graph button, so if you push second and then table, has a table of values. And because of what I did yesterday, my table is starting at 54. I'm really interested in what's happening between 0 and 15, but mine is starting at 54. So I could go up over and over and over again, and that might take a while. Or above your window button, it says table set. So if you go second window to table set, it says, where would you like your table to start at? So I'm going to start it at 0. And then when I go back to my table, now it's starting at 0. I can now look at the values between 0 and 10. And can you see that they go, looks like at 5, it's at 1500, which seems to be the biggest that my table of values shows up. So now I can go back to my window and say, instead of going up to 40,000, maybe 2,000 would be enough. And on my scale, maybe I'll go up by hundreds. So now when I graph, my graph looks more like my picture. Okay? Notice how the maximum's not right in between our two x-intercepts. I was telling my class, last period class yesterday, that you often suffer from parabolitis. That when you are drawing your graphs, you're so used to parabolas being symmetrical, and I did it here. I suffer strongly from parabolitis in that I made my maximum perfectly in the middle, just because people like symmetry. But in reality, in this one, as we can see from the graph, it's not perfectly in the middle. It's more to the left. So now that we've got our graph, you want to find that maximum. Second, calculate. Number 4 is maximum. We need to go to the left. We need to go to the right. The long way to go to the left is hitting your left button over and over again until you get there. The short way to go to your left is to know what your values of x on here, and since I know I've gone from 1 to 15, and pick a value that's left of your maximum. Can you see that if I choose x equals 2, so I just push 2, that would be to the left of my maximum. And when I push enter, my calculator draws a vertical line. Some of the older calculators just draw that arrow. Is that arrow to the left of my maximum? Yes, perfect. Instead of hitting to the right button until I get to the right, I'm going to look and say 2, 4, 6, probably 8 will be more than enough. Oh yeah. Is my maximum between those two lines? Yes. So on guess, you can just push enter again. And it's telling us that x should be 4.5 and y is 512. Now with these questions, you may have to go back and read part C over a couple of times, especially on the test, because they ask a lot of information. It says, to the nearest cubic centimeter, what is the maximum volume? So, in C, we can say our max volume is, I'll go back to my graphing calculator, well, my volume was my y, that's 1512, and because it's a word problem with units, you have to include your units. And this is what you're going to do on a test sometimes. You're going to be like, woohoo, I wrote something down, I answered it, let's move on to the next question. But in this part C, it asks 3 or 4 questions. So it's good practice when you do, this is good practice for any subject, but when you finish a question or think you finish a question, read that question again to make sure you've answered everything that it's asked for. So in this one, I answered to the nearest cubic centimeter, what is the maximum volume? What size of square should be cut? Oh, well, I haven't done that. So size of square, well, that would be my x by x. So I can go back to my graphing calculator and steal my x value. It's 4.5. I'm going to read it again because it says to the nearest, what size of square? It doesn't say. So, but the next one is nearest tenth. So I'm going to go 4.5 centimeter, a 4.5 centimeter by 4.5 centimeter square. And then again, you think you finished your question, but you read it again and it says, what are the dimensions to the nearest tenth of a centimeter? So our dimensions are 4.5 centimeters. Notice how I'm adding my units every single time here. If I take 4.5 centimeters off twice on the black side would be 21 centimeters. And on the red side, if I take off 9 centimeters, I'll get 16 centimeters. That is a lot of questions in that part. But I think this example and the thing that we did at the first, this is a great application of where is this useful? In a lot of businesses, finding a maximum of something or a minimum of something is super important. In fact, if you could figure out, for example, for Coca-Cola, if you could figure out how to save 1 cent off the making of every can of Coca-Cola, you could retire tomorrow because you would save that company billions of dollars, and then they would be more than happy to give you like $500 million and you'd be set for life, right? So if you could figure that out. But sometimes life is more complicated than that, right? Because, you know, you could probably save at least a cent if you said, oh, you just make the Coke can without a lid. But then there's practicality problems.
No, you just use slaves. You just use slaves, right? They'll pay, you save a few cents. Yeah.
But these ideas, this example gives you a sense of the practicality of some of these things. Finding maximums, finding minimums. This leads a lot into calculus. And so I feel like as far as a word problem and realistic use, this is very, very good. The next one is going to be an example of a word problem that's not useful at all, other than for practicing math. So here we go. Oh, I forgot to give you the questions for this one. We're going to leave everything for the end today. So 3, 4, 5, 6, 9, and 10.